myself Dr. P. Soumya, working as an assistant professor in the Department of Chemistry, Institute of Aeronautical Engineering College. In this session, I'm going to discuss about estimation of hardness of water. So in this session, I'm going to discuss about what is titration, what is standard solutions, what are standard solutions, so what is buffer, types of titrations, and finally estimation of hardness of water by using complexometric titration. So first we should know what is titration. So titration is also known as titrimetry and volumetric analysis. So the titration also known as titrimetry and volumetric analysis. So it is a common laboratory method. So which is used for the quantitative chemical analysis to determine the concentration of an identified analyte. So it is by using titration we can measure unknown concentration of unknown solution by using known concentration of solution. So here we will use burette and we will use a conical flask for the titration process. So here the solution which is known concentration is known as titrant. The solution of known concentration is called as titrant. This is usually taken in the burette. So this is burette. Usually we will take solution of known concentration. So that is also known as titrant. The solution of unknown concentration. So we will take in conical flask. This is conical flask. So we will take unknown solution in the conical flask. So this is called as analyte. So analyte is a substance which is being analyzed. So is called as analyte. So this can be taken in the conical flask while doing titration. So known concentration solution is taken in burette. So the total process, this process is called as titration. So by this titration, we will measure volumes of unknown solution. So here volumes, we will measure the endpoint of the reaction by using volumes. So this is also known as volumetric analysis. So volumetric analysis. So this is quantitative chemical analysis. Here we are measuring quantities. So quantities. So this is also called as quantitative chemical analysis. So what is indicator? While doing the titration, we can use indicators. So what is the use of indicator and what is indicator? So this indicator in a titration are used to identify the equivalence or end point of the reaction where pH change occurs. Here indicator, it indicates the end point or it indicates the equivalence or neutralization point of the reaction. So where pH change occurs. So this is definition of indicator. So what is end point? So what is end point? Here the point where the reaction between two solutions is just complete. The point where the reaction between the two solutions is just complete is called as end point. So other definition is the point where color changes occurs is called as end point of titration. So here we are using indicators for indicating the end point. So what is end point? The point where color changes occurs is called as end point of titration. So this is the terminology which is used in titration. So what is standard solution? Standard solution, it is solution whose concentration is precisely known. So standard solution is solution of known concentration or solution whose concentration precisely known. So that is called as standard solution. So we can use these solutions to determine the concentration of other unknown solutions. So by using standard solution, we will determine the concentration of unknown solutions. So this can be divided into two types. So first one is primary standard. Primary standard solutions and secondary standard solutions. Secondary standard solutions. So what is primary standard? What is primary standard? It is a compound of sufficient purity from which a standard solution can be prepared. It is a primary standard is a compound of sufficient purity and stability and from which the standard solution can be prepared by weighing of quantity of it followed by dilution to give defined volume of solution. To give defined volume of solution. So how to prepare a standard solution? So first we have to take a standard flask. So this is standard flask. So first we have to take known amount of substance. Known amount. So we have to weigh some amount, certain amount. We have to weigh and we have to pour in the standard flask. So this is standard flask which is used for the preparation of standard solutions. So after that we have to add water up to mark. So this is having one mark. Up to mark we have to add water. So here this is a standard solution. This is a standard solution. So like this we have to prepare standard solutions by using standard flask. So here what is primary standard? It is a compound of sufficient purity by which a standard solution can be prepared. So that is primary standard. So the primary standard should have high purity, high stability, high equivalent weight, not hygroscopic, and it should have low toxicity, it should be inexpensive, and it should be readily available. So the primary standard should have mostly high purity, high stability, low toxicity, not hygroscopic. So it not hygroscopic, it should not absorb the water. So it should not absorb the water. So that type of substance is called as primary standard. The type of substance is called as primary standard. It can be used as a primary standard solutions. So which is used for the determination of unknown concentrations of other solutions. So examples of primary standards are sodium carbonate. Usually we will use sodium carbonate, sodium oxalate, sodium tetraborate, and potassium dichromate, that is K2Cr2O7, potassium bromate. So these substances, these compounds are acts as primary standards, and these are used for the preparation of primary standard solutions. So what is secondary standard? So secondary standard is a substance which may be used for the standardizations and whose content of active substances has been found by comparison against the primary standard. It is the substances which is may be used for the standardizations. So the secondary standard is this is not stable. This is not stable, and this is not pure, and it can undergo it can be hygroscopic. So when we use these secondary standards, the concentration of secondary standards varies from time to time. So we have to standardize the secondary standards by using primary standards, because the primary standards are stable and they are low toxicity and highly pure, and they are not hygroscopic. So for primary standards, the concentration does not vary with the time. For secondary standard, the concentration varies with the time. So we have to standardize the secondary standard solutions by using primary standard solutions. So The secondary standard solution is a solution in which the concentration of dissolved solid has not been determined from the weight of the compound dissolved, but by the reaction of volume of solution against measured volume of primary standard solution. So which means, so we can know the concentration of secondary standard solution by using primary standard solution. By using primary standard solution. So examples of secondary standard solutions are HCl, HNO3, sodium hydroxide, potassium permanganate and silver nitrate. Hydrochloric acid, nitric acid, sodium hydroxide, KMnO4 and silver nitrate are the examples for the secondary standard solution. So we have to standard these solutions by using primary standards. By using primary standard solution when we are using in the titration. So before going to the titration, first we have to standardize. If we take HCl, we have to standardize the HCl by using primary standard solution. Then only we have to do titration. So what is buffer? So buffers is a solution is one which maintains its pH fairly constant even upon addition of small amount acid or base. It is a solution is one which maintains its pH constant even upon addition of small amount of acid or base. So this is a solution if we add small amount of acid or base, so the pH does not change. So this type of solution is called as buffer solution. This type of solution is called a buffer solution. So these again two types: acidic buffer, basic buffer. Acidic buffer and basic buffer. So acidic buffer is a solution of mixture of weak acid and salt of weak acid with a strong base. It is a solution of mixture of weak acid and salt of this weak acid with a strong base. Here we know that weak acid example is acetic acid. Here I am taking acetic acid example of weak acid. So when it is treated with strong base, so it will give salt CH3COONA and water. So the acidic buffer is a mixture of acetic acid and sodium salt of acetic acid. Sodium salt of acetic acid. So this is a result of so the acidic buffer is a solution of a mixture of weak acid and the salt of weak acid with strong base. So we will get some salt. So it is a mixture of weak acid and salt of weak acid with strong base is used as acidic buffer. So whereas basic buffer, it is a solution of mixture of weak base and salt of this weak base with a strong acid. So it is a mixture of weak base and the salt of weak base with a strong acid. Weak base with strong acid. So basic buffer is a mixture of weak base and salt of this weak base with a strong base. So types of titration. So depending on the types of reactions involved, the titrations can be classified as follows. So depending on the types of reactions involved, these titrations can be divided into 4 types. So first one is acid-base titration, redox titration, precipitation titration, complexometric titration. So acid-base titration, redox titration, precipitation titration and complexometric titration. So what is acid-base titration? So it is a acid-base titration is a technique to determine the concentration of acid or base solutions by neutralizing unknown concentration of solution with the known concentration of base or acid. So acid-base titration, it involves the acid-base neutralization. So it involves acid-base neutralization reaction. Neutralization reaction. So if we want to measure the unknown concentration of base, so we have to use acid. So we have to titrate against acid, and we should determine the concentration of base. Base. So base unknown. So we have to take base unknown. So we have to titrate against acid, and we have to know the concentration of base using the acid. So here, when this acid is titrated against base or base is titrated against acid, here one reaction is taking place, that is acid-base reaction, that is neutralization reaction. So for example, acid is HCl. When it is treated with NaOH, so it will form water and sodium chloride. So it is forming acid, base. So this is reacting with each other and forming salt and water. So this reaction is called as neutralization reaction. This reaction is called as neutralization here. So here pH is less than 7. Here pH is more than 7. pH is more than 7. So here water pH is 7. So here we are taking acid which is having less than 7 pH. So we are titrating against the sodium hydroxide which is having more than 7 pH. So we are titrating with each other. So we are forming water and salt. So these are having 7. So neutral. So here they are forming neutral pH. So this reaction is called as neutralization reaction. So that point is called as neutralization point or end point. So the neutralization reaction is determined by using indicator. So to know the end point, we have to use indicator in case of acid-base titrations. So this will change its color at the point of the titration. So for example, if we want to know the concentration of HCl, first we have to titrate against the sodium hydroxide. So if we take, so in this HCl, in this you have to take NaOH. So after certain point, so here we are also adding one indicator, HCl with indicator. So when we adding NaOH, so this HCl is reacting with the NaOH. After a certain point, so the color changes occurs. Here pink color. Here we are adding phenolphthalein indicator. If we take HCl, so we have to add phenolphthalein indicator. So when we add this indicator, so it will give, finally we will get pink color. So after reacting with, after completion of reaction, neutralization reaction between HCl and base, so this, after that, after certain point, this sodium hydroxide reacts with indicator and it will give pink color. So this is the end point. So we have to note down the burette volume as an end point. So this is about acid-base titration. Here, this method allows quantitative analysis of unknown acid or alkali. So this is also called as quantitative analysis, quantitative chemical analysis. So redox titration. It is also same as acid-base titration, except it involves redox reaction. In acid-base titration, acid-base reaction is taking place. In redox titration, redox reaction is taking place. So this generally does not require indicator. So reagents which are used in redox titrations are chosen so that the reaction is spontaneous and one half the reactions has a natural color change. Has a natural color change. So here I am taking iron sulfate KMnO4. So iron sulfate and KMnO4 in presence of acid like H2SO4. So here we are taking a PSO4 solution. So this is by adding H plus ions. So this is titrated against KMnO4. Finally, we will get pink color. Here we are not using any indicators, but we are getting color because KMnO4 it acts as a self indicator. It can act as a self indicator or own indicator. Self indicator or own indicator. So it will give color after end point. So when it reacts with iron sulfate, no color changes occurs. When iron sulfate is completed, so the KMnO4 color it will appear as a pink in the conical flask. So this is indicates the end point of the redox titration. So the KMnO4 can act as self indicator or own indicator. Third one is precipitation titration. Precipitation titration is a type of titration which involves the formation of precipitate during the titration technique. Precipitation titration is a type of titration which involves the formation of precipitate during the titration. So here in the precipitation titration, the titrant reacts with analyte and forms insoluble substances called precipitate. So while titration, so it will form precipitation. Throughout the titration, we will notice throughout the titration, we will get precipitation. So it is the type of titration which involves the formation of precipitate during the titration technique. So in this, the titrant reacts with analyte and forms insoluble substance called precipitate. So it continues till the last amount of analyte is consumed. It continues till the last amount of analyte is consumed. Means throughout the titration, we will notice the formation of precipitate, which is insoluble substance. So it is used to determine the concentration of metallic halides by using silver nitrate. It is used to determine the concentration of metallic halides, example sodium chloride, by silver nitrate. By silver nitrate. When this sodium chloride is treated with titrate against silver nitrate solution, so we will get AgCl precipitate. AgCl precipitate. So this type of titration is called as precipitation titration. Complexometric titration. So complexometric titration is a technique of volumetric analysis. So in which soluble, undissociated, stoichiometric complex is formed. In complexometric titration, so this involves the formation of soluble and undissociated stoichiometric complex formation. So during the titration, here in this complexometric titration, the formation of colored complex used to indicate the end point of the titration. In complexometric titration, so we will the formation of colored complexes indicates the end point of the titration. Here we are using indicator. In complexometric titration, we are using indicators. Complexometric titration, we are using indicators. So these complexometric titrations particularly useful for the determination of mixture of different metal ions in the solution. So this is useful for the determination of mixture of different metal ion in the solution. So an indicator capable of producing a definite color change usually used to detect the end point of the titration. So in complexometric titration is a titration. It is a volumetric analysis in which soluble undissociated complex is formed during the addition of titrant to the sample solution. So in this complexometric titration, we will use indicators to indicate the end point. So ethylene diamond, its next topic, estimation of hardness of water using complexometric titration. So for estimation of hardness of water, we will use complexometric titration. So in this, ethylene diamine tetraacetic acid, EDTA, used to determine the hardness of water with the help of complexometric titration. So here we are using EDTA. We are using EDTA. So this is ethylene. What is the structure of ethylene diamond? Ethylene diamine tetraacetic acid, CH3, CH2, COOH, CH2, COOH, CH2, COOH, CH2, COOH. So this is the structure of ethylene diamond tetraacetic acid. But in this titration, this is not soluble in water. This is not insoluble in water. This is not soluble in water. So we can use disodium salt of ethylene diamine tetraacetic acid. Here 2 hydrogens are replaced by 2 sodiums. So disodium ethylene diamine tetraacetic acid used as a titrant in the estimation of hardness of water. So we will use indicator, that is ABT indicator. ABT indicator. So the full form is iriochrome black tea. So this is the structure of iriochrome black tea. This is azo dye. This is azo dye. This is azo dye. So it can be used as an indicator in the complexometric titration. So we will use one buffer solution, that is ammonical buffer solution, to maintain the pH. To maintain the pH of the solution. So in this solution, we are using EDTA, iriochrome black tea, as an indicator, ammonical buffer as a buffer, basic buffer, which is used for the maintaining pH to 10. So what is the principle involved in the estimation of hardness of water? So the calcium plus 2 and magnesium plus 2. So we know that what is hardness? So hardness or hard water. So the water which contains the dissolved salts of calcium plus 2 and magnesium plus 2 is called as hard water, which cannot give lather with the soap. So it is containing calcium plus 2 and magnesium plus 2. So this is in water, it is responsible for the hardness. So these ions, the calcium plus 2 and magnesium plus 2 forms. So when this sample, this water sample, here we are taking water sample and we are adding ABT indicator, this will form complex, some selectable complex with the ABT indicator. So when this will form metal and indicator weak complex. This is wine red color. This is in wine red color. When we treat it with EDTA solution, so this EDTA will form strong complex with the metal ion. EDTA will form strong complex with the metal ion. So it will leave the free indicator by leaving the free indicator. So this is in the blue color. This is in the blue color. So we will get end point wine red to blue color. So when we add ABT indicator to the hard water solution, so we will get wine red color. After titration with the EDTA as a titrant, so we will get wine red to blue color. So that is indication of end point of this complexometric titration. So in this, in hard water, we are having calcium plus 2 and magnesium plus 2. These form first complex with EBT indicator. After that, when we are adding EDTA, this EDTA will form strong complex with the calcium plus 2 and magnesium plus 2 which are present in water, and by leaving the free EBT indicators. So, the metal stable complex and at pH 10. So, here we are adding buffer solution to maintain the pH. So, we are adding ammonical buffer to maintain the basic pH. So, at this pH only, the metal ion will form complexes with EBT and EDTA. So, that's why we are maintaining the pH using buffer solution. So, this is the reaction metal ion. So, this is indicated by metal M. So, metal ion, this is plus 2. So, this is indicated M plus 2. This is first reacting with EBT. Then it is forming metal EBT or metal indicator complex. So, this is wine red color. So, this is like this wine red color. So, whenever we are adding EDTA solution to wine red color metal indicator solution, the metal ions form more stable complexes with EDTA. So, this is the complex. So, this metal ion, it will form with EDTA complex. So, here we are, this is a bivalent metal, either calcium plus 2 and magnesium plus 2. This will form complex with the EDTA here. So, this is EDTA, nitrogens of EDTA, 2 nitrogens and 4 oxygens. 2 nitrogens and 4 oxygens are forming complex bonds, the coordination covalent bonds with the metal. So, here, so this EDTA, it is donating 6 lone pair of electrons, 6 lone pair of electrons to the metal, bivalent metal. So, this can act as hexadentate ligand. So, this is giving 6 lone pair of electrons to the metal ion to form the more stable complex. So, this can act as hexadentate ligand. So, this is the structure of complex formed by the metal ion and EDTA. So, when all the metals in the sample complexed with EDTA, further addition of EDTA. When all the metals in the sample replaced with the when the complex with the EDTA, the further addition of EDTA liberates the free indicator solution at pH 10. So, which it will give blue color. So, it indicates the end point of the titration, complexometric titration. So, here first when we add EBT indicator to the sample solution, we will get wine red color. So, last end point is blue colors. So, we will get blue color as an end point. So, procedure, how procedure of the complexometric titration. So, what is the procedure of complexometric titration? So, in this, first we have to take known volume of hard water, some 100 ml or 40 ml or 20 ml. So, like that, we have to take known amount, known volume of water sample, known volume of hard water sample, and we have to add 3 ml of buffer to maintain the pH. 3 ml of buffer and 4 to 5 drops of indicator. So, here we are using Aeronautical black tea indicator. First, we have to take the known volume of hard water sample. To this, we have to add 3 ml of buffer solution and 4 to 5 drops of indicator. This solution treated against standard EDTA solution. Against the standard EDTA solution. So, this endpoint of the color change is from wine red to blue. The endpoint is wine red to blue. So, the molarity of EDTA of solution is M2. So, here we are titrating with EDTA. So, we are This is water, we are titrating with EDTA. Here, the molarity of EDTA is taken as M2. The volume which is coming from burette, so which is observed in the burette, volume of burette, it is V2. So volume, the titer value or volume of EDTA from the burette, so that is V2 ml. V2 ml. So here the volume of hard water, we have taken known volume of hard water. Volume of hard water, it is V1. So we should know the concentration of hard water by using M1 equal to M2 V2 by V1. So we have to find out the concentration of hard water, concentration of metal ions which are present in hard water. So by using M1 equal to M2 V2 by V1. So after determining the molarity, so we should convert into ppm. So we will get in molarity. So to convert molarity into ppm, we have to multiply with 10 to the power of 5. So it will converts into ppm. So the total salts, the total number of salts which are dissolved in the hard water, this is also called as total hardness. Total hardness of hard water. Total hardness of hard water. So this is when from the first step we will get total hardness of sample. So by titrating hard water with the EDTA. Second step is, so first we have to take the known water sample in a beaker and we have to boil for half an hour. So after cooling it, it is filtered and the filtrate titrate against EDTA. So first we have to take some known volume of 100 ml. Here I am taking. So we have to take the water and we have to boil it. We have to heat it. So here heating. So we know that the temporary hardness will removed by the boiling, simple boiling. So here we are taking known volume of water and we are boiling for half an hour, for 30 minutes. And after that, so this is filtered. This is filtered. So the filtrate titrated. So filtrate, which is from the filtration. So the filtrate will titrated against the EDTA. So then, so we will get permanent hardness. By this titration, we will get permanent hardness because we are removing the temporary hardness by boiling and we are taking that water and we are titrating against EDTA. So after end point, we will get the burette reading that should be taken as titer value is taken as V2 ml and the molarity of EDTA is M3 and the hard water is V3. So here, so this is V3. The titer value is V3 and we should, so the EDTA molarity is M2. So this is V2. So the molarity already we have taken M2 as a molarity of EDTA, V2 as a titer value of EDTA, volume of EDTA, and the volume of hard water is V3 ml, that is known volume. So we know we have to find out the concentration of ions present in hard water. So that is nothing but permanent hardness of water because we are boiling the water to remove the temporary hardness. So we will get the total ion concentration by applying this formula M3 equal to M2 V2 by V3. M2 V2 by V3. So here from this we will get permanent hardness in ppm by multiplying with 10 to the power of 5. 10 to the power of 5. So from the first step we got total hardness of water. From the second step, we are getting permanent hardness of water. First step, step 1, we got temporary total hardness. From second step, we got permanent hardness. So, what is the temporary hardness of water? So, the temporary hardness of water equal to total hardness minus permanent hardness. So, by using this complexometric titration, we can estimate the total hardness water, temporary hardness of water, and permanent hardness of water. So this is the use of complexometric titration, which is used for the estimation of hardness water, that is total hardness, temporary hardness, and permanent hardness of water. Thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.